Tonight, we're going to explore one of the most unsettling contradictions in stellar astronomy. Imagine looking at a city where every building is ancient, crumbling, and worn down by billions of years of time. And then, right there in the middle of it all, you spot one building that looks brand new, freshly painted, gleaming, as if it were built yesterday. That's exactly what astronomers found when they looked closely at some of the oldest star clusters in our galaxy. Stars that have no business being young, sitting right next to stars that are clearly dying of old age. They're called blue stragglers. They shouldn't look the way they do, and figuring out why they exist forced astronomers to rethink what they thought they knew about how stars live and die. Before we dive in, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you already know, even if you've never really thought about it. Stars die. They don't last forever. The sun will not shine indefinitely. It had a beginning, it has a middle, and someday, billions of years from now, it will have an end. This is one of the most fundamental facts in all of astronomy. Stars are born, they burn, and eventually they run out of fuel and die. But here's what most people don't think about. Not all stars die at the same rate. Some stars burn through their fuel in just a few million years. Others last for trillions of years, far longer than the current age of the universe. And the thing that determines how long a star lives, the single most important factor, is something beautifully simple. It's mass. How much stuff the star is made of. That one number, the mass of a star at its birth, controls almost everything about its life. How hot it will be, how bright it will shine, what color it will glow, and most importantly, how long it will last before it dies. This relationship between mass and lifespan is one of the most important ideas in stellar astronomy, and understanding it is essential to understanding the mystery we're exploring tonight. Because the whole reason blue stragglers are so shocking, the whole reason they disturb astronomers so deeply, is that they seem to violate this relationship. They appear to break the rules of how stars are supposed to age. But before we can appreciate why that's so unsettling, we need to understand the rules themselves. Let's begin with what a star actually is. A star is, at its core, a battle, a constant war between two opposing forces. On one side, gravity. The star is an enormous ball of gas, mostly hydrogen, and all that mass is trying to collapse inward under its own weight. Gravity wants to crush the star into the smallest possible space. On the other side, energy. Deep inside the star's core, temperatures and pressures are so extreme that hydrogen atoms are being fused together into helium. This is nuclear fusion, the same process that powers a hydrogen bomb, except in a star it happens continuously, every second of every day, for millions or billions of years. This fusion releases an enormous amount of energy. That energy pushes outward, creating pressure that fights against gravity's inward pull. And as long as these two forces are balanced, the star remains stable. It shines, it holds its shape, it lives. This balance is called hydrostatic equilibrium, and it's one of the most important concepts in all of stellar physics. Every stable star you see in the night sky is in this state of balance right now. Gravity pulling in, fusion pushing out. The moment the balance breaks, the star begins to die. Now, here's where mass comes in. A more massive star has stronger gravity. That seems obvious, More stuff means more gravitational pull. But the consequence of that stronger gravity is not what you might expect. You might think a more massive star having more fuel would last longer. After all, a bigger gas tank should mean a longer trip, right? But that's not how stars work. A more massive star has more fuel, yes, but it also burns that fuel far, far faster. The extra gravity compresses the core more intensely, raising the temperature and pressure to extreme levels. And the rate of nuclear fusion doesn't just increase a little, it increases dramatically. The relationship between a star's mass and its luminosity, how much energy it produces, follows what astronomers call the mass-luminosity relation. For main sequence stars, the ones in the stable middle part of their lives, luminosity scales roughly as mass to the power of 3.5. That means if you double a star's mass, you don't double its energy output. You increase it by about 11 times. If you triple the mass, the energy output goes up by about 46 times. The star is burning through its fuel at a ferocious rate. This has a dramatic effect on lifespan. A star with 10 times the mass of our Sun doesn't live 10 times shorter. It lives roughly 300 times shorter. Our Sun has enough hydrogen fuel to last about 10 billion years. It's roughly halfway through that lifespan right now, about 4.6 billion years old, with another 5 billion or so to go. A star 10 times more massive than the Sun might live only about 30 million years. That sounds like a long time by human standards, but by cosmic standards, it's the blink of an eye. The universe is 13.8 billion years old. A 20 million year stellar lifespan is less than 0.2% of the age of the universe. These massive stars are born, they burn with incredible intensity, and they die almost immediately on the cosmic timescale. On the other end, a star with half the mass of the Sun could last for tens of billions of years. A star with 1/10 the Sun's mass, a tiny red dwarf, could burn for trillions of years. No red dwarf anywhere in the universe has ever died of old age. The universe simply hasn't been around long enough. Every single red dwarf that has ever formed in the entire history of the cosmos is still shining right now. So the pattern is clear. Massive stars are hot, blue, bright, and short-lived. Low-mass stars are cool, red, dim, and long-lived. Stars in between, like our Sun, fall somewhere in the middle. Yellow, moderately bright, with lifespans measured in billions of years. This is not a theory or a guess. It's observed fact. Astronomers have measured the properties of hundreds of thousands of stars and confirmed this relationship over and over again. Mass determines everything. Now, there's a tool that astronomers use to visualize all of this, and it's one of the most important diagrams in all of science. It's called the Hertzsprung-Russell diagram, named after two astronomers who developed it independently in the early 1900s. Einar Hertzsprung, a Danish astronomer, and Henry Norris Russell, an American astronomer. Both realized that if you plot stars on a graph with temperature on one axis and luminosity on the other, something remarkable happens. The stars don't scatter randomly, they fall into distinct patterns. The most prominent pattern is a long band stretching diagonally across the diagram, from the upper left to the lower right. This band is called the main sequence. The upper left corner of the main sequence contains the hottest, brightest, most massive stars. These are the blue and white giants, burning through their fuel at incredible rates. The lower right corner contains the coolest, dimmest, least massive stars. The red dwarfs, barely glowing, conserving their fuel over trillions of years. Our sun sits somewhere in the middle of this band, not the brightest, not the dimmest. A perfectly average star living a perfectly average stellar life. The main sequence is where stars spend most of their lives. As long as a star is fusing hydrogen into helium in its core, it stays on the main sequence. It's stable, it's in balance, but eventually every star runs out of hydrogen fuel in its core, and when that happens, it leaves the main sequence. It evolves. Depending on its mass, it might swell into a red giant or a red supergiant. It might shed its outer layers and become a white dwarf. It might explode as a supernova and leave behind a neutron star or a black hole. But the key point is this: when a star exhausts its core hydrogen, it moves off the main sequence. It leaves that diagonal band on the Hertzsprung-Russell diagram and migrates to a different part of the chart. And this is where star clusters become incredibly important. A star cluster is exactly what it sounds like: a group of stars that form together at the same time, from the same cloud of gas and dust. This is crucial. When a giant molecular cloud, a vast reservoir of hydrogen gas, begins to collapse under its own gravity, it doesn't form just one star. It fragments into hundreds, thousands, sometimes hundreds of thousands of smaller clumps, each one collapsing independently to form its own star. All of these stars are born at roughly the same time, within a few million years of each other. They're made of the same material, the same chemical composition. The only thing that differs between them is their mass. Some are born large, some are born small, most are born somewhere in between. Think of a star cluster as a cosmic laboratory. You have a population of stars that all start their lives at the same moment, but with different masses. And since mass determines lifespan, these stars will die in a predictable order. The most massive stars, the hot blue ones, will burn out first. They'll leave the main sequence within just a few million years. The medium mass stars will follow, leaving the main sequence after hundreds of millions or billions of years. And the lowest mass stars, the red dwarfs, will stay on the main sequence essentially forever. This gives astronomers an incredibly powerful tool. By looking at a star cluster and seeing which stars have left the main sequence and which ones are still on it, you can determine the age of the cluster. It's like a cosmic clock. Here's how it works. Imagine a very young cluster, just a few million years old. If you plot all its stars on a Hertzsprung-Russell diagram, you'd see the entire main sequence populated from top to bottom. The hot blue stars are still there. The cool red stars are still there. Everything in between is still there. Nobody has died yet because not enough time has passed for even the most massive stars to exhaust their fuel. Now fast forward a few 100 million years. The most massive stars have burned through their hydrogen. They've left the main sequence, swelling into red giants or exploding as supernovae. The upper portion of the main sequence is now empty. The hot blue stars are gone, but the lower part of the main sequence is still intact. The medium and low mass stars are still burning away. Now fast forward a few billion years. More stars have left the main sequence. The medium mass stars are now running out of fuel too. The main sequence has been eaten away from the top down like a candle burning from the top. The point on the main sequence where stars are just now beginning to leave, the boundary between stars that have exhausted their fuel and stars that haven't yet, is called the main sequence turn-off point. The turn-off point is everything. It tells you the age of the cluster. If the turn-off point is high up on the main sequence, among the hot, bright stars, the cluster is young. Not enough time has passed for many stars to die. If the turn-off point is low on the main sequence, among the cooler dimmer stars, the cluster is old. Many generations of massive and medium mass stars have already burned out. Only the small, slow-burning stars remain. This method of dating star clusters is called isochrone fitting, and is one of the most reliable techniques in all of astronomy. It works because the physics of stellar evolution is well understood. We know how long a star of a given mass should last. We know when it should leave the main sequence. We can predict, with remarkable accuracy, what a star cluster should look like at any given age. And for the most part, star clusters behave exactly as predicted. The old clusters look old. The young clusters look young. The turn-off point falls exactly where it should, based on the cluster's age. There are two main types of star clusters, and the distinction matters for our story. Open clusters are loose collections of a few hundred to a few thousand stars. They're found in the disk of the Milky Way, often near regions where new stars are still forming. Open clusters tend to be relatively young, typically a few 100 million years old, though some are older. They're not very tightly bound by gravity, so over time they tend to drift apart. The stars gradually scatter, spreading out into the general population of the galaxy. The Pleiades, also known as the Seven Sisters, is a famous open cluster about 444 light-years away. It contains over 1,000 stars, all about 100 million years old. Globular clusters are something else entirely. These are dense, spherical collections of hundreds of thousands, sometimes millions of stars, all packed into a relatively small volume. They're ancient. Most globular clusters in the Milky Way formed more than 10 billion years ago, making them nearly as old as the universe itself. Some are estimated to be 12 or even 13 billion years old. These clusters orbit the Milky Way in its halo, the vast spherical region surrounding the galaxy's disk. They're not part of the spiral arms. They're relics from the earliest era of the galaxy's formation, survivors from a time when the Milky Way was just beginning to take shape. The globular cluster Omega Centauri is one of the most spectacular. It contains roughly 10 million stars packed into a sphere about 150 light-years across. If you lived on a planet inside Omega Centauri, your night sky would be breathtaking. Thousands of stars visible to the naked eye, many of them bright enough to cast shadows. The sky would be a blaze of light, so dense with stars that true darkness would be almost impossible. 47. Tucanae is another impressive globular cluster, visible from the southern hemisphere. It contains several million stars and is roughly 12 billion years old. Some of its stars formed when the universe was less than 2 billion years old, making them among the most ancient objects we can observe anywhere in the cosmos. These are among the oldest objects we can observe anywhere in the cosmos. Now here's why globular clusters are so important for our story. Because they're old, extremely old. The main sequence turn-off point in a globular cluster is very low on the Hertzsprung-Russell diagram. All the massive blue stars burned out billions of years ago. All the medium mass yellow stars, like our sun, have also exhausted their fuel. The only stars still on the main sequence in a typical globular cluster are the low mass red and orange stars, the slow burners, the ones that conserve their fuel over enormous timescales. Everything above the turn-off point should be gone. Every star more massive, more luminous, hotter and bluer than the turn-off should have died a long time ago. They should have swelled into red giants, shed their outer layers, and collapsed into white dwarfs billions of years in the past. There should be nothing left in the upper part of the main sequence. Nothing hot and blue, nothing young looking. The cluster should look uniformly old. Every star in it should show the signs of extreme age: dim, cool, red or orange, quietly burning through the last of their fuel over timescales that stretch into the future for tens of billions of years more. This is what the physics predicts, and this is what astronomers expected to find when they started studying globular clusters in detail with modern instruments. A clean, orderly population of old stars, neatly following the rules of stellar evolution. The turn-off point sitting low on the Hertzsprung-Russell diagram. Nothing above it, nothing surprising. And for the most part, that's exactly what they found. The old globular clusters looked old. The turn-off points were right where they should be. The massive blue stars were gone. The predictions matched the observations beautifully. Stellar evolution theory was working perfectly. The models were confirmed, everything made sense, except for one thing. When astronomers looked more carefully, when they plotted every star in certain globular clusters onto the Hertzsprung-Russell diagram with precision, they noticed something that didn't fit. Something that shouldn't have been there. Sitting above the turn-off point in the part of the diagram that should have been completely empty, there were stars. Not one or two that might be dismissed as measurement errors. Dozens of them. Sometimes hundreds. Stars that were hotter than they should be. Bluer than they should be. More luminous than they should be. Stars that looked, by every measure, like they were young. As if they hadn't gotten the message that their cluster was billions of years old. As if they had somehow cheated time itself. These stars sat in a region of the Hertzsprung-Russell diagram where nothing should exist. Not in a cluster this old. The physics was clear. Stars of that mass and temperature should have burned out billions of years ago. They should have been dead. They should have been white dwarfs or scattered remnants, not bright, hot blue main sequence stars, shining as if they had just been born. And yet, there they were, unmistakable, undeniable, shining stubbornly in a place where the laws of stellar evolution said they had no right to be. They weren't passing visitors from somewhere else. Their chemistry matched the cluster. Their positions within the cluster confirmed they belonged there. They were members of this ancient population, born from the same cloud of gas that created every other star in the cluster over 10 billion years ago. And yet, they looked young. Impossibly, inexplicably young. This was not a minor puzzle. This was a direct challenge to one of the most well-established theories in astrophysics. If stellar evolution is correct, if mass determines lifespan, if the physics of nuclear fusion is well understood, then these stars should not exist. They should have died billions of years ago. Something was very, very wrong. Either the theory was broken, or something extraordinary had happened to these stars. Something that could reset their clocks. Something that could make an old star look young again. Astronomers had a name for these impossible objects. They called them blue stragglers, because they seemed to straggle behind, lingering in a youthful state long after they should have aged and faded like everything around them. And understanding what they really are, understanding how a star can appear to defy the fundamental relationship between mass and lifespan, would take decades of careful observation, creative thinking, and some of the most dramatic physics the universe has to offer. Because, as it turns out, the answer involves stars doing things to each other that astronomers once thought were almost impossible. Collisions, theft, cannibalism. In the dense, crowded hearts of the oldest star clusters in the galaxy, stars are not living quietly and dying alone. They're interacting, they're merging, they're stealing mass from each other in acts of stellar vampirism that can rejuvenate a dying star and give it a second life it was never supposed to have. But to understand how that works, we first need to understand exactly what these blue stragglers look like, exactly where they were found, and exactly why their discovery shook the foundations of what astronomers thought they knew about the oldest stars in the universe. The year was 1953. An astronomer named Allan Sandage was working at the Palomar Observatory in Southern California, studying one of the most beautiful globular clusters visible from the northern hemisphere. It was called Messier 3, a dense ball of roughly 500,000 stars sitting about 34,000 light-years from Earth in the constellation Canes Venatici, the hunting dogs. Messier 3 was already well known to astronomers. It had been catalogued back in 1764 by the French astronomer Charles Messier, who was actually looking for comets at the time and kept a list of fuzzy objects in the sky that weren't comets, so he wouldn't confuse them with what he was actually searching for. That catalogue, the Messier catalogue, became one of the most important lists in astronomy. And while Messier 3 was the third entry on the list, it holds a special distinction. It was the first object that Messier himself actually discovered, rather than recording from earlier observers. By the time Sandage turned his attention to it in the early 1950s, astronomers had a decent understanding of what globular clusters were. They knew these were ancient collections of stars, all roughly the same age, all born from the same original cloud of gas. They knew the physics of stellar evolution well enough to predict what the Hertzsprung-Russell diagram of such a cluster should look like. They knew the massive blue stars should be gone. They knew the turn-off point should be low. They expected Messier 3 to look old, uniformly old, because it was old, roughly 11 to 12 billion years old, give or take. Sandage carefully measured the brightness and colour of individual stars in Messier 3 and plotted them on a Hertzsprung-Russell diagram. And for the most part, the cluster behaved exactly as expected. The main sequence was truncated. The hot, bright, massive stars were gone, exactly as predicted. The turn-off point sat right where the theory said it should for a cluster of this age. Stars above the turn-off had evolved off the main sequence and become red giants, moving to the upper right part of the diagram. Everything was orderly, predictable, and consistent with the laws of stellar evolution. Except for one thing. Above the turn-off point, scattered in a region of the diagram that should have been completely empty, Sandage found a group of stars that didn't fit. These stars were bluer, hotter, and more luminous than anything that had a right to exist in this ancient cluster. They sat on or near the main sequence, but above the turn-off point, in a zone where every star should have died billions of years ago. They looked like main sequence stars of much higher mass, the kind of stars that should have burned out when the Earth was still young, when dinosaurs hadn't yet evolved, when complex life on our planet was barely getting started. And yet here they were, still shining, still hot, still blue, still very much alive. Sandage called them blue stragglers. The name was simple, almost casual. They were blue, meaning hot, and they were stragglers, meaning they seemed to have fallen behind, lagging in a youthful state long after the rest of the cluster's population had aged and moved on. The name stuck, and it perfectly captured the essential weirdness of these stars. Everything around them had aged normally. The cluster's other stars had followed the rules, burning through their fuel at the rate their mass dictated, leaving the main sequence when their time was up, evolving into red giants and white dwarfs right on schedule. But the blue stragglers hadn't followed the rules. They were still sitting on the main sequence, burning hydrogen in their cores, looking for all the world like young, vigorous stars in the prime of their lives. They were stragglers in the truest sense, left behind while everyone else moved on. Let me be very precise about what a blue straggler looks like, because the physical details matter enormously. A blue straggler is a star that sits above and to the left of the main sequence turn-off point on the Hertzsprung-Russell diagram of its host cluster. Above means it's more luminous, producing more energy. To the left means it's hotter, with a higher surface temperature. In practical terms, a typical blue straggler might have a surface temperature of around 7,000 to 10,000 degrees Kelvin, compared to the 5,000 to 6,000 degrees that characterize the stars at the turn-off point in an old globular cluster. It might be 2 to 3 times more luminous than the turn-off stars. And crucially, it might have a mass of roughly 1.2 to 1.7 times the mass of our Sun, while the turn-off mass in its host cluster might be only about 0.8 to 0.9 solar masses. This is the heart of the problem. In an old globular cluster, any star born with a mass of 1.2 solar masses or higher should have exhausted its core hydrogen billions of years ago. It should have swelled into a red giant, shed its outer layers, and collapsed into a white dwarf. It should not still be on the main sequence. It should not still be burning hydrogen. It should not still be hot and blue. And yet, the blue stragglers are doing exactly that. They appear to be main sequence stars with masses well above the cluster's turn-off mass. If you didn't know they were members of an ancient cluster, if you just looked at them in isolation, you would conclude they were relatively young stars, maybe 1 or 2 billion years old, still in the early or middle stages of their hydrogen-burning lives. But they're not young. They can't be young. The cluster they belong to is 11 or 12 billion years old. Star formation in globular clusters ended billions of years ago. There is no gas left in these clusters to form new stars. The raw material was used up long ago, consumed by the original burst of star formation that created the cluster in the first place. There are no stellar nurseries hiding inside globular clusters. No regions of active starbirth, no fresh hydrogen clouds collapsing to form new generations of stars. Whatever is in the cluster now is what was made at the beginning. And that means the blue stragglers were made at the beginning too. They were born with the rest of the cluster over 10 billion years ago. But if they were born over 10 billion years ago, and if they have masses above the turn-off mass, then they should be dead. The physics is clear. A star with 1.5 times the mass of the Sun should last roughly 3 billion years. Not 11 billion. It should have burned out 8 billion years ago. There is no way a star of that mass, burning hydrogen through normal fusion, could still be alive after 11 billion years. The fuel simply wouldn't last that long. It would be like finding a candle still burning a week after you lit it, when you know for certain it only had enough wax to last a few hours. Something doesn't add up. When Sandage first published his findings, the astronomical community took notice. This wasn't a marginal observation or a controversial interpretation. The data were clear. The stars were there. They were members of the cluster. And they were in the wrong place, on the Hertzsprung-Russell diagram. It is worth pausing to appreciate what Sandage's work actually involved, because the discovery didn't arrive in a flash of sudden revelation. It was ground out slowly, painstakingly, through months of meticulous labor. In the early 1950s, astronomical observations weren't made with digital cameras or computer screens. They were made with photographic plates, glass sheets coated with a light-sensitive emulsion that captured the faint glow of distant stars during long exposures through the telescope. Sandage would spend hours at the telescope, guiding the instrument by hand, making sure it tracked the sky precisely enough to keep the starlight focused on a single point of the plate. A single exposure could take 30 minutes or more. Then the plate had to be developed, like a photograph in a darkroom, and examined under a microscope. Each star appeared as a tiny dot on the plate. To measure a star's brightness, Sandage had to compare the size and darkness of that dot to calibration stars with known brightnesses. To measure a star's color, he had to take multiple exposures through different colored filters, then compare the brightness of each star in each filter. The whole process was done by hand, star by star, dot by dot. For a cluster like Messier A3, which contains hundreds of thousands of stars, Sandage couldn't measure them all. He focused on the brightest and most accessible ones, carefully building up his Hertzsprung-Russell diagram one data point at a time. And it was there, sitting at his desk with the diagram taking shape in front of him, that the anomaly became impossible to ignore. The main sequence cut off exactly where theory predicted. The red giant branch was populated exactly as expected. Everything was orderly and clean, except for those stubborn points scattered above the turnoff. Too blue, too bright, sitting where nothing should be. Sandage was careful. He double-checked his measurements. He re-examined the plates. He considered whether the points might be artifacts, errors in the photographic process, blemishes on the emulsion. They weren't. The stars were real, and they were in the wrong place. The question was not whether blue stragglers existed. The question was how. How could a star appear younger than the population it belonged to? How could it sit above the main sequence turn-off in an ancient cluster? What physical process could create a star that looked like it had been born recently in an environment where no new stars had formed for billions of years? The initial reaction was cautious. Some astronomers wondered if the blue stragglers might be imposters, stars that weren't actually members of the cluster but happened to be in the line of sight, appearing to be inside the cluster when they were really much closer to us or much farther away. This was a reasonable concern. When you look at a globular cluster, you're looking through the galaxy, and there are foreground and background stars that can contaminate your observations. But careful follow-up studies eliminated this possibility. Astronomers measured the velocities of the blue stragglers and found that they matched the velocities of the other cluster stars. They were moving with the cluster at the same speed, in the same direction. Stars that happened to be in the line of sight, but were not part of the cluster, would have different velocities. The blue stragglers were genuine members. Other astronomers wondered if the blue stragglers might be stars that had been captured by the cluster, young stars from the galactic disk that had wandered into the cluster's gravitational field and been pulled in. But this didn't work either. Globular clusters orbit the Milky Way in the halo, far above or below the galactic disk where young blue stars live. The chances of a young disk star being captured by a halo globular cluster are essentially zero. The orbits don't cross in the right way, the velocities don't match, and the geometry makes it nearly impossible. Besides, detailed chemical analysis of the blue stragglers showed that their compositions, the relative amounts of different elements in their atmospheres, match the composition of the other stars in their clusters. They had the same metallicity, the same ratios of iron to hydrogen, the same patterns of element abundances. These stars were made from the same material as everything else in the cluster. They belonged there. They were natives, not immigrants. Another possibility was that these stars were simply ordinary cluster members that had been misidentified. Maybe they weren't really above the turn-off point. Maybe the color or brightness measurements were wrong. But as telescopic technology improved through the 1960s, 70s, and 80s, the observations only became sharper and more definitive. Better instruments confirmed that the blue stragglers were exactly where they appeared to be. Above the turn-off, hotter than they should be, bluer than they should be. The measurements were not wrong. The stars were real, and they needed an explanation. After Sandage's discovery in Messier A3, astronomers began looking for blue stragglers in other clusters, and they found them everywhere. Virtually every globular cluster that was studied carefully enough turned out to contain blue stragglers. Messier A13, the great globular cluster in the constellation Hercules, had them. 47 Tucanae, the spectacular cluster visible from the southern hemisphere, had them. Omega Centauri, the largest globular cluster in the Milky Way, had them. NGC 6397 had them. NGC 5466 had them. Messier A30 had them. Cluster after cluster after cluster, the same pattern repeated. An ancient population of old stars, with a clearly defined turn-off point, and then a scattering of anomalous blue stars sitting above it, defying the predictions of stellar evolution. The numbers varied from cluster to cluster. Some clusters had only a handful of blue stragglers. Others had dozens or even over 100. But the phenomenon was universal. Blue stragglers were not a quirk of one particular cluster. They were not caused by some local peculiarity of Messier 3's environment. They were a general feature of old stellar populations. Whatever was creating them was something fundamental, something that operated in every dense cluster of ancient stars. And it wasn't just globular clusters. As astronomers expanded their search, they found blue stragglers in open clusters too. These are the younger, looser collections of stars found in the galactic disk. Open clusters like Messier 67 at roughly 4 billion years old, and NGC 188 at nearly 7 billion years old. Two of the oldest known open clusters also contained stars sitting above their main sequence turn-off points. The same anomaly appeared in the younger populations. Stars that looked too hot and too blue for their age, sitting in places on the Hertzsprung-Russell diagram where they had no business being. This was an important clue. Whatever process was creating blue stragglers, it wasn't unique to the extreme environments of globular clusters. It also happened in the less dense, less extreme environments of open clusters. This meant the explanation couldn't rely solely on the extreme stellar densities found in globular cluster cores. There had to be at least one formation mechanism that could operate in lower density environments as well. Astronomers even found blue stragglers in the field population of the Milky Way. among stars that weren't part of any cluster at all. These field blue stragglers were harder to identify because you needed to determine the star's age independently. But spectroscopic analysis could reveal stars that appeared younger than their chemical composition suggested they should be. A star with very low metallicity, very few heavy elements, almost certainly formed early in the universe's history, when the Milky Way was young and heavy elements were scarce. If such a star appeared hot, blue, and luminous, it was a blue straggler candidate. It looked young but was chemically old. The same contradiction, the same impossible youthfulness, showing up in yet another environment. The universality of the phenomenon was both exciting and daunting. Exciting because it meant blue stragglers were telling us something important about stellar physics, something fundamental that we hadn't fully understood. Daunting because it meant any explanation had to be robust enough to work across a wide range of environments, from the incredibly dense cores of globular clusters to the relatively sparse populations of open clusters and the galactic field. By the 1970s and 80s, the blue straggler puzzle had become one of the central problems in stellar astrophysics. The observations were solid, the stars were real, they belonged to their clusters, and they appeared younger than the populations they were embedded in. The data were pointing toward a conclusion that was, when you really thought about it, astonishing. These stars must have somehow gained mass after they were born. They didn't start out as massive, hot blue stars. If they had, they would have burned out billions of years ago, like all the other massive stars in the cluster. Instead, they must have started out as ordinary low-mass stars, below the turn-off mass, burning slowly and quietly, like all their neighbors. And then, at some point during the cluster's long history, something happened to them. Something that added mass to them. Something that transformed them from ordinary, unremarkable, low-mass stars into the hot blue, overluminous anomalies we see today. Think about what that means. These stars weren't born special. They weren't formed from some unusual pocket of gas with different properties. They were ordinary stars that had something extraordinary happen to them. They were low-mass stars that somehow acquired enough additional mass to jump above the main sequence turn-off point, reigniting as hotter, brighter objects. In a very real sense, they were rejuvenated. They were given new fuel, their clocks were reset. This idea that blue stragglers gained mass after their initial formation was the breakthrough insight. It shifted the question from how can a massive star survive so long, which has no satisfying answer within normal stellar physics, to how can a low-mass star gain mass, which is a question that does have physical answers. Stars are not isolated objects floating in empty space, especially in star clusters, where densities can be incredibly high. Stars interact with each other. They pass close to one another. They orbit each other in binary systems. They feel each other's gravity. And under the right conditions, these interactions can transfer mass from one star to another, or even cause two stars to merge into a single, more massive object. The Hubble Space Telescope transformed our understanding of blue stragglers when it began observing globular clusters in the 1990s. Hubble's sharp vision could resolve individual stars in the dense cores of globular clusters in ways that ground-based telescopes simply couldn't. From the ground, the cores of globular clusters appeared as a blur of light, with individual stars hopelessly merged together. Hubble could separate them, measuring the brightness and color of each star individually. and what Hubble revealed was striking. In cluster after cluster, blue stragglers were found concentrated in the cores, the densest central regions where stars are packed most tightly together. This made sense if stellar interactions were responsible. The denser the environment, the more opportunities for stars to collide or exchange mass. The cores of globular clusters are among the densest stellar environments in the entire galaxy. Stars in these regions pass within a few stellar radii of each other on a regular basis. Close encounters are common. Collisions, while still rare by everyday standards, happen often enough over the life of a cluster to produce a population of merged stars. But Hubble also found something unexpected. In some clusters, the blue stragglers were not only concentrated in the core, there was also a secondary concentration of blue stragglers in the outer regions of the cluster, far from the dense core. The distribution was bimodal, with lots of blue stragglers in the middle, fewer at intermediate distances, and then more again in the outskirts. This was puzzling. If blue stragglers were formed by collisions, they should only be found in the core because collisions require high densities. The blue stragglers in the outskirts couldn't have been created by collisions. The stellar density out there was far too low for stars to run into each other with any meaningful frequency. Something else was creating blue stragglers in the outer regions of these clusters. And that something else was almost certainly binary stars. Binary star systems, two stars orbiting each other, are incredibly common. Roughly half of all stars in the Milky Way are in binary or multiple star systems. In star clusters, the fraction can be even higher. And in a binary system, something remarkable can happen. When one star evolves and expands, swelling into a red giant, it can overflow a critical gravitational boundary called the Roche lobe. The Roche lobe is the region of space around each star in a binary system within which material is gravitationally bound to that star. When the expanding star overflows its Roche lobe, its outer gas layers are no longer bound to it. Instead, that gas streams across to the companion star, falling onto its surface, adding to its mass. The companion star gains mass. It gets heavier. And as it gets heavier, it gets hotter and bluer, climbing up the main sequence in the Hertzsprung-Russell diagram. If enough mass is transferred, the companion can be pushed above the main sequence turnoff point, becoming a blue straggler. This process doesn't require high stellar densities. It doesn't require collisions. It just requires a binary system where one star evolves faster than the other, which is guaranteed to happen if the two stars have different masses. The more massive star evolves first, expands, overflows its Roche lobe, and donates mass to its lighter companion. The companion, now fattened with stolen hydrogen, burns hotter and bluer than it ever would have on its own. It looks younger. It looks more massive. It looks like a star that has no business being alive in an old cluster. It is a blue straggler. This binary mass transfer channel explained the blue stragglers found in the outer regions of clusters, where collisions were too rare to be effective. And it also explained blue stragglers in open clusters and in the galactic field, environments where stellar densities are far lower than in globular cluster cores. You don't need a crowded environment for mass transfer in a binary. You just need two stars orbiting each other closely enough for one to share its material with the other. And there was direct evidence for this pathway. Astronomers discovered that some blue stragglers had companions that were white dwarfs, the remnant cores of stars that have shed their outer layers. This was exactly what the mass transfer model predicted. The donor star, the one that gave away its mass, would evolve into a white dwarf after losing its outer layers. The recipient star, now bloated with stolen mass, would appear as a blue straggler. And when you observe the system, you would find a blue straggler orbiting a white dwarf. This is precisely what was found in multiple clusters. The smoking gun, a blue straggler sitting next to the corpse of the star it had fed on. Other blue stragglers showed chemical signatures consistent with mass transfer. When a star evolves and its core burns through different nuclear fusion stages, the products of that burning can be mixed into its outer layers. If those outer layers are then transferred to a companion, the companion's atmosphere will contain unusual chemical signatures, elements, or isotope ratios that don't match what you would expect from a normal main sequence star. Some blue stragglers showed exactly these signatures: elevated levels of carbon or nitrogen, or unusual isotope ratios that betrayed the fact that their surface material hadn't always been theirs. It had come from somewhere else, from a companion star that had processed it through nuclear burning before passing it along. So by the turn of the 21st century, the picture was becoming clearer. Blue stragglers are not genuinely young stars. They are old stars that have been rejuvenated through mass gain. They started their lives as ordinary low-mass members of their host clusters, quietly burning hydrogen, following the same evolutionary path as all their neighbors. But at some point during the cluster's history, something happened. Either they collided with another star, merging into a single, more massive object, or they were part of a binary system and received mass from an evolving companion. Either way, the result was the same. They gained mass. Their cores were provided with fresh hydrogen fuel. They became hotter, bluer, and more luminous, climbing above the main sequence turn-off point, and appearing to be far younger than the ancient population surrounding them. They didn't break any laws of physics. They didn't violate stellar evolution theory. They just found a loophole. A way to add mass to a star after it was born, effectively resetting its evolutionary clock and giving it a second life it was never supposed to have. The rules of stellar evolution still applied. Mass still determined lifespan. A star of 1.5 solar masses still couldn't last 11 billion years. But a star that was born at 0.8 solar masses and then had 0.7 solar masses dumped onto it at some later point, that star could absolutely appear as a 1.5 solar mass main sequence star today. It wouldn't have been burning at that mass for the cluster's entire lifetime. It would have spent most of its life as a quiet, low-mass star, and then, relatively recently in cosmic terms, been transformed into something hotter and brighter. The turn-off point in its cluster says that any star above 0.8 solar masses should be dead. But the blue straggler wasn't above 0.8 solar masses for the whole life of the cluster. It only recently became that massive. It cheated the clock by gaining mass late in the game. And that, in essence, is what a blue straggler really is. It's a star that appears younger than it should because something happened to increase its mass after it was born. It's not genuinely young. It's rejuvenated, rebuilt, given new fuel that extends its life beyond what its original birth mass would have allowed. It's sitting in a part of the Hertzsprung-Russell diagram where it has no right to be, shining with a youthful vigor that seems impossible given the ancient age of its surroundings. And the question that drove astronomers for decades, the question of how these stars could still exist in populations billions of years old, turns out to have answers that are as dramatic as the question itself. Answers involving stellar collisions and mass theft, and binary evolution in some of the most extreme environments in the galaxy. The stars that shouldn't still exist do exist, and the reason they exist tells us something profound about how stars live and die, not in isolation, but in the company of other stars, in environments where the crowded, chaotic, gravitational dance of hundreds of thousands of suns can create objects that no single star could ever become on its own. Now that we know what blue stragglers are, stars that appear impossibly young because they've somehow gained mass after their original formation, the real question becomes how? How does a star actually gain mass in the middle of its life? What physical process can take an ordinary, aging, low-mass star and transform it into something hotter, bluer, and more luminous? The answer, as it turns out, comes in two main flavors, and both of them involve stars doing extraordinary things to each other. Things that only happen when stars live in close quarters, whether packed together in the dense cores of ancient clusters, or locked in tight orbital embrace with a companion. The first mechanism is the most dramatic, the most violent, the most conceptually stunning. Two stars physically collide and merge into one. Now, in most of the universe, stellar collisions essentially never happen. Stars are tiny compared to the distances between them. Even inside a galaxy with hundreds of billions of stars, the space between those stars is so vast that the chance of two of them running into each other is almost zero. Consider our own stellar neighborhood. The nearest star to our Sun is Proxima Centauri, about 4.24 light-years away. That's roughly 40 trillion kilometers of empty space between us and our closest neighbor. If you shrunk the Sun down to the size of a grain of sand, Proxima Centauri would be another grain of sand roughly 18 miles away. 2 grains of sand separated by 18 miles of empty space. The chances of them colliding are laughably small. Even over billions of years, even accounting for the fact that stars move relative to each other, collisions between stars in the general galactic field are so rare that they essentially don't happen. The galaxy is just too empty. The stars are just too far apart. The odds are vanishingly small. But globular clusters are different, radically different. The cores of globular clusters are among the most crowded stellar environments in the entire galaxy. In the center of a typical globular cluster, you might find tens of thousands of stars packed into a volume just a few light years across. The stellar density in these cores can be thousands or even tens of thousands of times higher than in the solar neighborhood. Stars are much, much closer together. Instead of being separated by light years, stars in a globular cluster core might be separated by only a few thousand astronomical units, a few thousand times the distance from the Earth to the Sun. That's still a lot of space, but it's orders of magnitude less than the distances between stars in the galactic disk. And these stars aren't sitting still. They're moving. Each star in the cluster is orbiting the cluster's center of mass, pulled by the combined gravity of all the other stars. Typical velocities are around 10 to 20 kilometers per second. At these speeds, in these densities, close encounters between stars become common over the lifetime of a cluster. Not every encounter results in a collision, of course. Most close encounters are just gravitational interactions where two stars pass near each other, deflect each other's orbits slightly, and continue on their way. But over billions of years, in a cluster containing hundreds of thousands of stars, the probability of actual physical collisions becomes significant. Astronomers have calculated that a dense globular cluster might experience a stellar collision roughly once every few 100,000 to a few million years. That might sound rare, but over the 10 to 12 billion year lifetime of a typical globular cluster, that adds up to thousands or even tens of thousands of collisions across the cluster's entire history. So, what actually happens when two stars collide? This is where computer simulations become essential, because obviously no human has ever witnessed a stellar collision up close. We can't recreate one in a laboratory, but we can model the physics using powerful computers, and astronomers have been doing exactly that since the 1980s. The technique most commonly used is called smoothed particle hydrodynamics, or SPH. In an SPH simulation, each star is represented by thousands or even millions of virtual particles, each one carrying mass, energy, temperature, and chemical composition information. The simulation tracks how these particles interact under the forces of gravity and gas pressure, step by step, second by second, as two stars approach each other and merge. The results are spectacular. When two sun-like stars collide at the velocities typical of a globular cluster core, the initial impact is remarkably gentle by cosmic standards. Stars aren't solid objects. They're balls of gas, mostly hydrogen and helium. When they first touch, the outer atmospheres interpenetrate. Gas from one star mixes with gas from the other. The merged material heats up from the collision, releasing energy. A shock wave propagates through both stars. Within hours, the two stellar cores spiral toward each other, sinking into the center of the growing combined mass. Material is flung outward in tidal tails and streams. Some of this material escapes into space entirely, lost to the merger, but most of it falls back, settling into a single, larger, more massive star. The whole process, from first contact to the formation of a single stable object, takes only a few hours to a few days. That's extraordinarily fast by astronomical standards. A star that took millions of years to form from a collapsing gas cloud can be fundamentally transformed in a matter of hours through a collision. And the result is a star that is more massive than either of the two original stars. Not quite as massive as both combined, because some material is always lost during the merger, but substantially more massive than either progenitor. Here's the crucial part. When the two stars merge, their hydrogen fuel gets mixed together. Each of the original stars had already been burning hydrogen in its core for billions of years, but each still had significant reserves of unburned hydrogen in its outer layers. Main sequence stars burn hydrogen only in their cores. The outer envelope contains plenty of unused fuel, but under normal circumstances, that fuel never reaches the core. It just sits there, unused, for the star's entire life. But during a collision, the violent mixing stirs up the entire structure of both stars. Hydrogen that was sitting unused in the outer layers gets mixed down toward the core. Fresh fuel reaches the nuclear burning region. The merged star effectively gets a new supply of hydrogen to burn, not because new hydrogen appeared from nowhere, but because hydrogen that was already there but inaccessible has been stirred into the mix. This is why the merged star looks young. It has a fresh supply of hydrogen fuel in its core, enough to sustain nuclear fusion for a significant period of time. Its mass has increased, pushing it higher on the main sequence. Its temperature has increased, making it hotter and bluer. It sits above the turn-off point of its cluster, shining with a luminosity that seems impossible for a star in such an old environment. But it hasn't violated any laws of physics. It has just redistributed its fuel through the most violent stirring mechanism imaginable, a head-on collision with another star. The simulations also reveal something interesting about the structure of collision products. Merged stars don't look exactly like normal stars of the same mass. A normal star of 1.4 solar masses that formed from a collapsing gas cloud would have a specific internal structure, a specific density profile from a core to surface, a specific distribution of hydrogen and helium. A collision product of the same total mass has a different internal structure. The mixing during the collision doesn't produce a perfectly uniform distribution of elements. Some regions are more mixed than others. The core might be slightly different in composition. The rotation rate is often much higher than normal because the orbital angular momentum of the two original stars gets converted into spin during the merger. Some collision products are expected to rotate much faster than ordinary stars of the same mass. These structural differences are subtle, but they're potentially detectable. Astronomers have looked for signs of rapid rotation in blue stragglers, and in some cases they've found it. Blue stragglers in some clusters rotate significantly faster than normal main sequence stars of similar mass, consistent with the collision hypothesis, but the evidence is mixed. Not all blue stragglers rotate rapidly, which suggests that either the rotation slows down over time through magnetic braking and other processes, or that not all blue stragglers were formed through collisions. There's another complication worth mentioning. Stars in globular clusters don't always collide head-on. In fact, head-on collisions are relatively rare. Most collisions are actually grazing encounters, where the two stars pass close enough to touch, but don't hit each other squarely. In these cases, the stars may not merge on the first pass. Instead, they lose energy through tidal interactions, become gravitationally bound to each other, and spiral inward over subsequent orbits until they eventually merge. These delayed mergers can take thousands or even millions of years after the initial encounter, but the end result is the same. A single, more massive star formed from the combination of two smaller ones. Some collisions don't even involve two single stars. In many cases, one or both of the colliding objects is part of a binary system. When a single star encounters a binary, the gravitational interaction can be incredibly complex. The single star might replace one of the binary members, kicking it out and taking its place, or the encounter might cause the binary members to spiral inward and merge with each other. Or all three stars might interact in a chaotic dance that ends with two of them merging, while the third is flung away at high speed. These three-body interactions are actually very important for producing blue stragglers in globular clusters. Binary systems are more likely to be involved in encounters than single stars because they present a larger cross-section. A binary system occupies more space than a single star, making it a bigger target for incoming stars. And the gravitational interactions in three-body encounters can extract energy from the binary, causing the two binary members to spiral closer together and eventually merge. This is called a dynamically induced merger, and it may be one of the most common pathways to producing blue stragglers in the dense cores of globular clusters. Now let's turn to the second major formation mechanism: mass transfer in binary systems. This pathway doesn't require the dramatic violence of a collision. It operates more slowly, more subtly, like a quiet theft rather than a head-on robbery. But it's no less remarkable, and it may actually produce more blue stragglers overall than collisions do. Picture two stars orbiting each other. They were born together from the same fragment of a collapsing gas cloud. They've been orbiting each other for billions of years, locked together by gravity. One star is slightly more massive than the other. Not dramatically more massive, maybe 1.0 solar masses versus 0.8 solar masses. They're both below the cluster's turn-off mass. Both are still on the main sequence. Both are burning hydrogen quietly and unremarkably. But the slightly more massive star is aging faster, because mass determines lifespan. It's burning through its fuel just a little bit more quickly than its lighter companion. Eventually, the heavier star exhausts the hydrogen in its core. It begins to evolve off the main sequence. Its core contracts and heats up while its outer layers expand. The star swells, growing larger and larger, becoming a red giant or subgiant. Its outer atmosphere puffs up, extending farther and farther from the core, reaching outward toward its companion. Now, in a binary system, each star has a region of gravitational dominance around it called the Roche lobe, named after the 19th century French mathematician Edouard Roche, who first calculated these shapes. The Roche lobe defines the volume within which material is gravitationally bound to that particular star. If a gas particle is inside star A's Roche lobe, it will stay with star A. If it crosses the boundary between the two Roche lobes, it enters star B's territory and will fall towards star B instead. The boundary between the two Roche lobes meets at a single point called the inner Lagrangian point, a point of gravitational equilibrium between the two stars. When the evolving star swells as a red giant, its expanding outer atmosphere can reach the edge of its Roche lobe. And when it reaches that boundary, something extraordinary happens. Gas from the expanding star spills over the edge of the Roche lobe, through the Lagrangian point, and falls towards the companion star. A stream of hydrogen-rich material flows from the evolving donor star to the unevolved companion. The companion star gains mass. This process is called Roche lobe overflow, and it's one of the most important phenomena in binary star astrophysics. It's responsible for a huge range of exotic objects in the universe, from blue stragglers to certain types of supernovae to X-ray binaries. The mass transfer doesn't happen all at once. It can continue for millions of years as the donor star gradually sheds its outer layers onto its companion. The rate of transfer depends on many factors: how fast the donor star is expanding, how close the two stars are, how their orbit responds to the mass transfer. In some cases, the transfer is stable. Material flows at a steady rate, and the binary system adjusts its orbit to accommodate the changing mass distribution. In other cases, the transfer can become unstable, with material flooding across at an ever-increasing rate until the two stars are engulfed in a common envelope of shared gas. This common envelope phase can lead to a merger, connecting this pathway back to the collision mechanism. But in the stable transfer scenario, the result is a blue straggler in the making. The companion star, originally the lighter member of the binary, gradually accumulates mass from its partner. As its mass increases, it becomes hotter and bluer, climbing up the main sequence. If enough mass is transferred, the companion crosses the turn-off point of its cluster, entering the forbidden zone on the Hertzsprung-Russell diagram. It becomes a blue straggler. Meanwhile, the donor star, stripped of its outer layers, contracts down into a white dwarf, the exposed spent core of what was once a normal star. The end result is a binary system consisting of a blue straggler and a white dwarf companion. The blue straggler is the rejuvenated star, fattened with stolen hydrogen, burning hotter and bluer than it should. The white dwarf is the corpse of the star that donated its mass, the victim of the theft. This is why some astronomers have called this process stellar vampirism. The blue straggler feeds on its companion, draining it of its substance to fuel its own continued existence. The observational evidence for this pathway is compelling. Astronomers have used the Hubble Space Telescope and ground-based spectroscopic surveys to study blue stragglers in detail, searching for the telltale signs of binary companions. And in many cases, they found exactly what the mass transfer model predicts: blue stragglers orbiting white dwarf companions. The orbital periods range from a few days to several years, consistent with the closed binary systems where Roche-Loeb overflow would occur. The white dwarf companions are often difficult to detect because they're much fainter than the blue straggler, but their presence can be inferred from the blue straggler's orbital motion, or from the faint ultraviolet excess they contribute to the system's light. In the open cluster NGC 188, one of the oldest known open clusters at about 7 billion years old, astronomers conducted a comprehensive survey of blue stragglers and found that the vast majority of them were in binary systems. This was powerful evidence that mass transfer was the dominant formation channel in this relatively low-density environment. Collisions would be extraordinarily rare in an open cluster because the stellar density is so much lower than in a globular cluster core. But binary mass transfer can happen regardless of the surrounding density. All you need is two stars in a sufficiently close orbit, and the normal course of stellar evolution will bring one of them to the point where it overflows its Roche-Loeb. In globular clusters, the picture is more complex. Both mechanisms appear to operate simultaneously. The collision channel dominates in the dense core, where stellar encounters are frequent enough to produce mergers. The mass transfer channel operates throughout the cluster, in both the core and the outskirts, wherever suitable binary systems exist. This dual-channel picture elegantly explains the bimodal radial distribution of blue stragglers that Hubble observations revealed in clusters like MESS-EA3 and MESS-EA30. The blue stragglers concentrated in the core are predominantly collision products, formed through direct mergers or dynamically induced mergers driven by three-body encounters. The blue stragglers found at larger distances from the center are predominantly binary mass transfer products, formed through Roche-Loeb overflow in binary systems that have always lived in the less dense outer regions of the cluster. There's also a third pathway that has gained attention in recent years, and it involves not two stars, but three. Triple star systems, three stars gravitationally bound to each other, can undergo complex orbital interactions that drive the inner binary to merge. The mechanism is called the Cozy-Leidov effect, named after the two physicists who independently described it. In a hierarchical triple system where two stars orbit each other closely while a third star orbits the pair at a greater distance, the gravitational influence of the outer star can gradually change the orbit of the inner binary. Specifically, it can drive the inner binary's orbit to become more and more eccentric, more and more elongated, until the two inner stars pass so close to each other at closest approach that they collide or that tidal forces cause them to spiral inward and merge. The Cozy-Leidov mechanism is particularly interesting because it can operate in relatively low-density environments where direct collisions would be rare. You don't need a crowded globular cluster core for this to work. You just need a triple star system with the right orbital geometry. This mechanism might contribute significantly to blue straggler formation in open clusters and in the galactic field, where collisions are too rare but triple systems are relatively common. Now, one of the most important questions astronomers have tried to answer is, which pathway dominates? Are most blue stragglers formed through collisions or through mass transfer? The answer appears to depend on the environment. In the dense cores of massive globular clusters, collisions and dynamically induced mergers are probably the dominant channel. The stellar density is high enough for direct encounters to be frequent, and binary systems in the core are constantly being disrupted and reshaped by interactions with passing stars. But across the cluster as a whole, and especially in lower density environments like open clusters in the field, mass transfer in binary systems is almost certainly the dominant pathway. Most blue stragglers, most of the time, are probably formed through the quiet theft of hydrogen from a binary companion rather than through the spectacular violence of a direct collision. Chemical evidence supports this picture. Blue stragglers formed through mass transfer should show specific chemical anomalies in their atmospheres. When a star evolves up the red giant branch, nuclear reactions in its deep interior produce certain elements and isotopes that get mixed into its outer layers through a process called dredge-up. When those chemically processed outer layers are then transferred to a companion, the companion's atmosphere becomes contaminated with these unusual elements. The signature is subtle, but detectable. Some blue stragglers show elevated abundances of carbon, and certain heavy elements produced through a process called the slow neutron capture process, which occurs in the deep interiors of evolving red giants. These chemical fingerprints are a direct record of mass transfer history. They tell us that the blue straggler's surface material didn't always belong to it. Some of it came from a companion star that had already undergone advanced nuclear processing. Collision products, on the other hand, shouldn't show these particular chemical signatures. When two main sequence stars collide, neither of them has undergone advanced nuclear burning in its deep interior. The collision mixes ordinary hydrogen-rich material from the outer layers of both stars. The resulting merger product should have a relatively normal surface composition, perhaps with some anomalies from the shock heating during the collision, but not the specific signatures of deep nuclear processing that mass transfer products show. Astronomers have used these chemical diagnostics to identify the formation pathway of individual blue stragglers. In some clusters, the chemical signatures clearly point to mass transfer. In others, the signatures are more consistent with collisions. And in many cases, a cluster contains both types, with some blue stragglers showing transfer signatures and others not, confirming that both pathways are active simultaneously. The orbital properties of blue stragglers provide additional evidence. Mass transfer blue stragglers should be in binary systems with white dwarf companions, as we discussed. Collision products, however, might or might not be in binary systems. If two single stars collide, the product is a single star. If a star in a binary collides with a passing single star, the product might be a binary or a single star, depending on the details of the interaction. And if a binary merger is driven by the Cozy-Leadov mechanism in a triple system, the merger product should still have the distant third companion orbiting it. By carefully cataloguing which blue stragglers are in binary systems, what orbital periods they have, what types of companions they have, and what chemical signatures they show. Astronomers have been able to build a detailed picture of how blue stragglers form in different environments. The picture is complex and not yet complete, but the broad outlines are clear. Blue stragglers are formed through interactions between stars, either violent mergers or gradual mass transfer, and the relative importance of each mechanism depends on the density and dynamics of the stellar environment. One more piece of evidence deserves attention. In Messier A30, a globular cluster that underwent a dramatic event called core collapse, where the cluster's core contracted to extremely high density, astronomers found an unusually large population of blue stragglers concentrated in the very center of the cluster. This was consistent with the expectation that the extreme density of a collapsed core would dramatically increase the collision rate. More collisions means more blue stragglers. The cluster's dynamical history had left its fingerprint on the blue straggler population. Similarly, in 47 Tucanae, one of the most massive and best-studied globular clusters, the blue straggler population has been mapped with extraordinary precision. The bimodal distribution is clearly visible, with a central concentration and a secondary population in the outskirts, exactly matching the dual-channel prediction. The blue stragglers near the center show properties consistent with collision or dynamically induced merger origins, while those in the periphery show properties more consistent with binary mass transfer origins. What emerges from all this work is a picture of blue stragglers as windows into the dynamical lives of star clusters. They're not just stellar oddities or astrophysical curiosities. Each blue straggler is a record of an interaction that took place somewhere in the cluster's history. A collision that happened 3 billion years ago. A mass transfer event that unfolded over 50 million years. A triple star system that was driven to merger by the Cozy-Lidov mechanism 700 million years ago. Every single blue straggler has a story. Every single one is evidence of the fact that star clusters are not static collections of isolated stars burning quietly and dying alone. They are living, dynamic systems where stars interact, collide, exchange mass, and transform each other in ways that individual stars in isolation could never experience. The blue straggler population of a cluster encodes information about the cluster's collision rate, its binary fraction, the density of its core, and the dynamical interactions that have shaped it over billions of years. By studying blue stragglers, astronomers can learn about the internal dynamics of clusters in ways that would be impossible by studying normal stars alone. Blue stragglers are probes. They are diagnostic tools. They are the fossils of stellar interactions, preserved in the Hertzsprung-Russell diagram for us to find and decode. And the physics that creates them, the collision physics, the mass transfer physics, the three-body dynamics, all of it is operating right now, today, in globular clusters throughout the Milky Way and beyond. Right now, at this very moment, somewhere in the core of some ancient globular cluster, two stars are spiraling toward each other, about to collide and merge into a new blue straggler. Somewhere else, in the outskirts of another cluster, a quiet binary system is undergoing Roche-Lobe overflow, with hydrogen streaming from an expanding red giant onto its smaller companion, gradually building a new blue straggler over millions of years. These processes are happening continuously. Blue stragglers are not relics of the past. They are being created right now. The population we see today is a snapshot, a frozen moment in an ongoing process of stellar interaction and transformation that has been operating for billions of years and will continue for billions more. The two pathways, collisions and mass transfer, work together to produce a population of stars that shouldn't exist by the simple rules of single-star evolution. Stars that burn too hot, shine too bright, and glow too blue for their ancient surroundings. Stars that have been given a second chance at youth through the most extreme processes the stellar universe has to offer, and understanding how they were formed has opened a window into the hidden dynamical lives of the oldest star clusters in the galaxy, revealing a universe that is far more interactive, far more violent, and far more creative than the simple picture of isolated stars quietly burning and dying would suggest. So we've arrived at the deeper question. We know what blue stragglers are. We know how they form. But why should we care? Why do astronomers devote so much time, so many telescope hours, so many research papers to studying these anomalous stars? The answer goes far beyond simple curiosity. Blue stragglers are not just weird stars that break expectations. They are among the most powerful diagnostic tools in modern astrophysics. They reveal things about star clusters, about stellar evolution, and about the dynamics of dense stellar systems that would be almost impossible to learn any other way. Every blue straggler is a message from the past, a record of something that happened inside a star cluster, encoded in the star's mass, its position, its chemical composition, its orbital properties, and its companions. And learning to read those messages has transformed how we understand the most ancient stellar structures in the galaxy. Let's start with what blue stragglers tell us about cluster dynamics. A globular cluster is not a static object. It's a living, evolving gravitational system where hundreds of thousands of stars are constantly interacting. Stars exchange energy through gravitational encounters. Some stars speed up and migrate outward, others slow down and sink toward the center. This process, called dynamical relaxation, gradually reshapes the cluster over time. The heaviest objects tend to sink toward the center, a phenomenon called mass segregation. Lighter objects tend to flow outward. This redistribution of mass changes the density profile of the cluster, the distribution of stars from center to outskirts, in ways that evolve over billions of years. Blue stragglers are directly affected by this process. Because they're more massive than the typical stars in their cluster, heavier than the turn-off mass stars that make up the bulk of the population, they experience mass segregation. They sink toward the center over time. The rate at which they sink depends on their mass, on the density of the cluster, and on how long ago they were formed. A blue straggler that was created 8 billion years ago has had plenty of time to sink toward the center. One that was created only a few 100 million years ago may not have sunk very far yet. This means the radial distribution of blue stragglers in a cluster, how they're spread out from center to edge, contains information about when they were formed. Astronomers have used this insight to probe the dynamical history of clusters in remarkable detail. By measuring where the blue stragglers are and comparing that distribution to what computer simulations predict, they can estimate the rate at which the cluster has been undergoing dynamical relaxation. They can figure out how dynamically evolved the cluster is, how much mixing and rearrangement has occurred since the cluster formed. In some clusters, the blue stragglers are almost entirely concentrated in the core. This suggests the cluster is highly dynamically evolved. Enough time has passed for mass segregation to drag most of the blue stragglers to the center. In other clusters, blue stragglers are still spread throughout, suggesting the cluster is less dynamically evolved. or that many of its blue stragglers were formed relatively recently and haven't had time to sink yet. The blue straggler distribution has become a kind of dynamical clock, a way to measure how much internal mixing a cluster has undergone. This is extraordinarily valuable because the dynamical state of a cluster is otherwise very difficult to determine. You can't watch a cluster evolve in real time. These processes take millions or billions of years, but the blue stragglers preserve a record of that evolution in their positions, and astronomers can read it. Blue stragglers also tell us about the binary star population inside clusters, and this is important because binaries are notoriously difficult to study in globular clusters. The dense, crowded cores make it hard to resolve individual stars, let alone identify which ones are in binary systems. But blue stragglers formed through mass transfer must have been in binary systems. If you find a blue straggler with a white dwarf companion, you know the binary existed. You know approximately how close the two stars were because Roche-Lobe overflow only occurs in relatively close binaries. You can estimate the masses of both components. You can infer properties of the original binary system before mass transfer began. Each mass transfer blue straggler is a window into the binary population of the cluster, telling you that at least one closed binary system existed with certain orbital properties. By studying the fraction of blue stragglers that are in binaries, and by measuring the properties of those binaries, astronomers can estimate the overall binary fraction of the cluster, the percentage of stars that have companions. This is a fundamental number for understanding cluster dynamics, because binaries play a crucial role in a cluster's evolution. Binary systems act as energy sources. When a single star encounters a binary, the gravitational interaction can extract energy from the binary's orbit, transferring kinetic energy to the single star and kicking it outward. This process, called binary burning, helps support the cluster against gravitational collapse. Without binaries injecting energy into the system, the cluster's core would contract more rapidly. The rate of binary burning depends on how many binaries the cluster has and how closely they orbit. Blue stragglers help astronomers constrain these numbers. The more mass transfer blue stragglers a cluster has, the more close binaries it must contain. The properties of those blue stragglers, their masses, their orbital periods, the masses of their white dwarf companions, all of these provide specific constraints on the binary population that are difficult to obtain any other way. Blue stragglers also serve as probes of stellar evolution theory itself. The standard models of single-star evolution are well tested and highly successful. They accurately predict the luminosities, temperatures, lifespans, and evolutionary paths of isolated stars across a wide range of masses. But blue stragglers are not products of single-star evolution. They are products of binary evolution or stellar mergers, processes that are much more complex and much less well understood. The models for binary evolution, for mass transfer through Roche-Lobe overflow, for common envelope evolution, and for merger dynamics are all areas of active research where significant uncertainties remain. Blue stragglers provide observational tests of these models. When astronomers predict how a mass transfer blue straggler should look, what its mass should be, what its surface temperature should be, what chemical signatures it should carry, what kind of companion it should have, and then compare those predictions to actual observations. They're testing the physics of binary evolution. When the predictions match, the models gain credibility. When they don't match, the models need to be revised. This iterative process of prediction and comparison drives improvements in our understanding of some of the most complex processes in stellar astrophysics. For example, early models of mass transfer predicted that blue stragglers formed this way should have very specific ratios of carbon to nitrogen on their surfaces, reflecting the nuclear processing that occurred in the donor star's interior before the material was transferred. Observations confirmed these predictions in some cases, but not all, leading astronomers to refine their models of how material is mixed during transfer and how much processing occurs before the transfer begins. The blue stragglers were the testing ground. Without them, these models would remain unchecked. One of the most fascinating recent discoveries involves the relationship between blue straggler populations and cluster properties. Astronomers have found that the number of blue stragglers in a cluster does not scale simply with the number of stars. You might expect that a cluster with twice as many stars would have twice as many blue stragglers, but it doesn't work that way. The relationship is more complex. Some massive clusters have fewer blue stragglers relative to their total population than smaller clusters. This anti-correlation puzzled astronomers for years. The explanation appears to be connected to the dynamical state of the cluster. In very massive, very dense clusters, the rate of dynamical interactions is so high that binary systems get disrupted before they can undergo mass transfer. Passing stars gravitationally perturb the binaries, widening their orbits or breaking them apart entirely. Fewer intact close binaries means fewer opportunities for mass transfer, which means fewer mass transfer blue stragglers. This insight reveals something profound about the interplay between stellar dynamics and stellar evolution. The same dense environment that promotes collisions and mergers simultaneously suppresses the binary mass transfer channel by destroying the binaries before they can do their work. The two formation pathways are not independent. They compete with each other, and the balance between them depends on the specific properties of each cluster. This has implications that extend far beyond blue stragglers themselves. The disruption of binary systems in dense clusters affects the production of other exotic objects as well, including millisecond pulsars, cataclysmic variable stars, and low-mass X-ray binaries. All of these objects require close binary systems to form, and all of them are affected by the same dynamical processes that create and destroy the binaries that produce blue stragglers. By studying blue stragglers, astronomers learn about the broader ecosystem of exotic objects and globular clusters, an entire zoo of strange stars and stellar remnants created by the same fundamental interactions. There's another dimension to this story that deserves attention. Blue stragglers have been found not only in star clusters, but also in dwarf galaxies. Several of the Milky Way's satellite dwarf galaxies contain populations of stars that appear bluer and more luminous than the ancient main sequence turnoff of their dominant old population. These field blue stragglers in dwarf galaxies raise interesting questions. In a dwarf galaxy, the stellar density is much lower than in a globular cluster core. Collisions are essentially impossible. So if blue stragglers exist in dwarf galaxies, they must have formed through binary mass transfer or possibly through the Kozier-Lidov mechanism in triple systems. Their presence tells us that binary evolution is operating in these galaxies and producing rejuvenated stars, just as it does in clusters. But there's a complication. In some dwarf galaxies, the apparent blue straggler population might not be entirely composed of genuine blue stragglers. Some of those blue stars might actually be genuinely younger. Unlike globular clusters, which stopped forming stars very early. Some dwarf galaxies have had extended or episodic star formation histories. A few stars that look like blue stragglers might actually be legitimately young stars born during a late burst of star formation. Disentangling the true blue stragglers from the genuinely young stars requires careful analysis of stellar spectra, chemical abundances, and spatial distributions. This ambiguity reminds us that identifying blue stragglers depends entirely on knowing the age of the population they're embedded in. In a globular cluster, where the age is well determined and star formation ended long ago, a star above the turnoff is clearly anomalous. In a dwarf galaxy with a more complex star formation history, the interpretation is less straightforward. Now, let me address one of the most common misconceptions about blue stragglers. The title of tonight's exploration says, "They shouldn't still exist." But this phrasing deserves careful clarification. Blue stragglers are not physically impossible. They don't violate any known laws of physics. There is nothing supernatural or paradoxical about them in the deepest sense. They are perfectly consistent with the laws of gravity, thermodynamics, nuclear physics, and fluid dynamics. The reason people say they shouldn't exist is that they violate a simpler expectation. The expectation that stars in an old cluster should all look old. This expectation is based on the model of single-star evolution, where each star is born with a certain mass and then evolves in isolation, following a predictable path from birth to death without any outside interference. Under that model, yes, blue stragglers shouldn't exist. A star born with 1.4 solar masses in a cluster that formed 12 billion years ago should have died roughly 9 billion years ago. Its presence on the main sequence today is impossible under the single star model. But the single star model is an idealization. Real stars, especially stars in dense clusters, do not live in isolation. They interact. They collide. They exchange mass. They transform each other. And when you allow for these interactions, blue stragglers become not just possible, but expected. They're a natural consequence of stellar dynamics in dense environments. The surprise is not that blue stragglers exist at all. The surprise is that it took astronomers so long to figure out why they exist, and that figuring it out required understanding not just how individual stars evolve, but how populations of stars interact with each other over billions of years. This distinction matters. It's the difference between saying the universe is doing something impossible and saying the universe is doing something that our simplified models didn't predict. Blue stragglers are a triumph of the second kind. They showed astronomers that the simple model of isolated stellar evolution, while powerful and largely correct, was incomplete. Stars don't just evolve, they interact. And those interactions can produce objects that look completely wrong from the perspective of simple models, but are perfectly natural from the perspective of a more complete understanding. There are still significant uncertainties in our understanding of blue stragglers. Despite decades of research, several important questions remain open. One of the biggest is the relative contribution of each formation channel. In any given cluster, what fraction of blue stragglers were formed through collisions, what fraction through binary mass transfer, and what fraction through the cozy lead-off mechanism in triple systems. The bimodal radial distributions and chemical diagnostics have given us broad answers, but the details are still debated. Different studies of the same cluster sometimes reach different conclusions depending on what assumptions are made about the cluster's dynamical history, its initial binary fraction, and how efficiently mass transfer operates. Another open question is why some clusters have many blue stragglers while others have few. The anti-correlation between blue straggler frequency and cluster mass is well established, but the exact physical explanation is still being refined. The disruption of binaries in dense environments is certainly part of the story, but there may be other factors at play. The cluster's initial concentration, its orbit around the Milky Way, whether it has undergone core collapse, its initial mass function, the distribution of stellar masses at birth, all of these properties might influence the blue straggler population in ways that are not yet fully understood. One particularly puzzling case is the globular cluster MESS-EA80, located about 32,000 light-years from Earth in the constellation Scorpius. MESS-EA80 has one of the densest cores of any globular cluster in the Milky Way, and it contains an unusually large population of blue stragglers. Astronomers have counted more than twice as many blue stragglers in MESS-EA80 as in other clusters of comparable mass. The core is so dense that stellar collisions are expected to occur more frequently here than in almost any other cluster, which could explain the surplus. But the numbers are still higher than even the most optimistic collision models predict, which suggests something else might be going on. Perhaps the cluster has an unusually high binary fraction. Perhaps it underwent a recent episode of core collapse that temporarily drove the density even higher than it is today. Perhaps there are formation pathways operating here that we haven't fully accounted for. Nobody knows for certain yet. At the other extreme, some clusters appear to have surprisingly few blue stragglers relative to what models predict for their mass and structure. Certain sparse, low-concentration globular clusters show blue straggler populations that fall below theoretical expectations, and these deficits are difficult to explain. If such clusters formed with fewer binary systems to begin with, that could suppress the mass transfer channel. But it remains unclear why one cluster would form with significantly fewer binaries than another of similar mass and age. These outliers, the clusters with too many blue stragglers and the clusters with too few, are among the most valuable objects for testing our theories. They sit at the edges of our models, in the places where our assumptions are most likely to break down and where new physics or new dynamical processes might reveal themselves. Future observations, particularly with the next generation telescopes, capable of resolving individual stars even deeper into the crowded cores of globular clusters, may finally explain what makes these outlier clusters different. There's also the question of how blue stragglers evolve after they're formed. A blue straggler doesn't stay on the main sequence forever. It's still burning hydrogen in its core, and eventually it will exhaust that fuel and evolve off the main sequence, just like any other star. But because it has an unusual internal structure, different from a normal star of the same mass, its post-main sequence evolution might be different too. It might become a red giant with slightly different properties. It might leave behind a white dwarf with an unusual mass or composition. Tracking the later evolutionary stages of blue stragglers is an active area of research that could reveal additional insights into the physics of stellar structure and nuclear burning. And there's the broader question of what blue stragglers in different environments have in common and how they differ. Blue stragglers in globular clusters, open clusters, dwarf galaxies, and the galactic field are all produced by stellar interactions. But the specific mechanisms and their relative importance vary from environment to environment. A complete theory of blue straggler formation needs to account for all of these populations simultaneously, explaining not just how individual blue stragglers form, but why the overall blue straggler population has the properties it does across the full range of stellar environments in which they're found. These are not idle questions. They connect to some of the deepest problems in astrophysics. How do dense stellar systems evolve over cosmic time? How do binary stars interact and transform each other? How does the environment in which a star lives affect its fate? Blue stragglers sit at the intersection of all these questions. They're small in number, but enormous in significance. Tiny anomalies that encode vast amounts of information about the systems that produce them. Let me step back now and think about what blue stragglers mean in a broader sense, beyond the technical details of stellar physics and cluster dynamics, because there is something genuinely profound about these stars, something that goes beyond equations and diagrams and telescope observations. Consider what a globular cluster really is. It's one of the oldest structures in the galaxy. Some globular clusters formed more than 12 billion years ago, when the Milky Way was barely taking shape, when the universe itself was young. These clusters have survived for an almost incomprehensible length of time. They've orbited the galaxy hundreds of times. They've watched the Milky Way's spiral arms form and reform. They've witnessed billions of years of cosmic history unfold around them while they persisted, ancient and enduring. And throughout all that time, the stars inside these clusters have been interacting with each other, exchanging gravitational energy, perturbing each other's orbits, occasionally colliding, occasionally stealing mass from each other. The cluster is not a museum of frozen objects. It's a living system, constantly evolving, constantly producing new configurations and new objects through the slow grinding of gravitational dynamics. Blue stragglers are the visible evidence of that hidden dynamical life. They are the proof that something has been happening inside these ancient clusters, something beyond simple stellar aging. They are the markers of events, collisions, mergers, mass transfer episodes that would otherwise leave no visible trace. Without blue stragglers, we might look at a globular cluster and see only a collection of old, fading stars quietly winding down toward death. We might conclude that nothing interesting has happened in these clusters for billions of years. Blue stragglers tell us that conclusion would be wrong. Plenty has been happening. Stars have been crashing into each other. Binary systems have been feeding mass from one partner to another. Triple systems have been driven to merge through complex gravitational choreography. The clusters have been alive with activity, producing new objects and reshaping their populations continuously. We just couldn't see it until we learned to read the evidence written in the anomalous blue stars scattered above the turn-off point. There's also something poetic about the concept of stellar rejuvenation. The idea that a star can be given a second chance. In the simple model of stellar evolution, every star has one life. It's born, it burns, it dies. Its fate is sealed at birth by its mass. There's no way to cheat, no way to extend your time, no way to escape the inexorable ticking of the nuclear clock. But blue stragglers show us that under the right circumstances, a star can get more time. Not through any violation of physics, but through interaction with another star. By colliding and merging, by receiving mass from a companion, a star can be reborn. It can be given fresh fuel. It can be pushed back up the main sequence, returning to a state of youthful vigor long after it should have begun to fade. It doesn't get a new life in any metaphysical sense. It's still the same collection of atoms, still following the same physical laws, but it gets more time, more fuel, more light, a few more billion years of burning before it finally exhausts its resources and dies for real. This is a reminder that the universe is more creative than we sometimes give it credit for. Our models are powerful, but they're simplifications. They capture the dominant behavior, the main story of how stars live and die. But the universe is richer than any model. It finds ways to produce objects and outcomes that our models didn't predict. Not because the models are wrong, but because they don't include every possible interaction, every possible pathway, every possible event that might occur over 13 billion years of cosmic history. Blue stragglers were one of the first major hints that stellar populations are not simply collections of independent objects evolving in isolation. They showed us that stars influence each other, that the environment matters, that a star's fate depends not only on its own properties, but on the company it keeps. This insight, which seems obvious in retrospect, was genuinely surprising when blue stragglers were first discovered. The single star model was so successful, so elegant, so predictive, that it was easy to assume it told the whole story. Blue stragglers showed it didn't. And this lesson extends far beyond astronomy. In many fields of science, the behavior of a system cannot be understood by studying its individual components in isolation. You have to understand how the components interact, how they influence each other, how the environment shapes outcomes. Blue stragglers are a case study in this principle, played out on a cosmic stage with actors made of hydrogen and helium and governed by the laws of gravity and nuclear physics. Tonight, we've taken a journey through one of the most fascinating puzzles in stellar astronomy. We started with the fundamental rules of how stars age, rules that seem simple and universal. Mass determines lifespan. Hot blue stars die young. Cool red stars last forever. In an old star cluster, the massive stars should be gone, leaving only the slow burners behind. Then, we discovered that some stars break these rules. Blue stragglers, stars that appear younger, hotter, and bluer than anything in their ancient cluster should be. Stars sitting in a region of the Hertzsprung-Russell diagram that should be empty. Stars that seem to defy the passage of time. We explored how they do it, not through any violation of physics, but through the most dramatic interactions the stellar universe has to offer. Head-on collisions in the crowded cores of globular clusters. Two stars smashing together and merging into one, their fuel mixed and redistributed, creating a single, rejuvenated star. Quiet mass theft in binary systems, one star siphoning hydrogen from its expanding companion, growing hotter and bluer at the companion's expense, becoming a stellar vampire feeding on its partner to extend its own life. Complex gravitational choreography in triple systems, where the Cozier-Lidov mechanism drives inner binaries to merge through the patient gravitational influence of a distant third companion. And we've seen why these stars matter beyond their own strange existence. They are probes of cluster dynamics, revealing how these ancient systems evolve and reshape themselves over billions of years. They are tracers of binary populations, exposing the hidden partnerships between stars that are otherwise almost impossible to detect. They are tests of stellar evolution theory, challenging our models of mass transfer and merger physics, and forcing us to refine our understanding of some of the most complex processes in astrophysics. They are markers of interactions, preserving a record of events that occurred millions or billions of years ago, events that would otherwise leave no visible trace. The title of tonight's journey asked why blue stragglers shouldn't still exist. And now you know the answer. They shouldn't exist under the simple expectation that every star in an old cluster should look old. That expectation assumes stars evolve in isolation, untouched by their neighbors, following a lonely path from birth to death, determined solely by the mass they were born with. Blue stragglers show us that this expectation, while mostly correct, is incomplete. Some stars don't die on schedule. Some stars get a second chance. Not because the universe makes exceptions, but because the universe is more dynamic, more interactive, and more creative than the simple model suggests. Stars collide. Stars feed on each other. Stars are reborn. And the evidence of these extraordinary events is written in the light of blue stragglers, shining defiantly above the turn-off point in some of the oldest star clusters in the cosmos. The next time you see a photograph of a globular cluster, a dense ball of ancient light containing hundreds of thousands of stars, remember that hidden inside that glow are a few dozen stars that have no business being there. Stars that are too hot, too blue, too luminous for their age. Stars that should have died billions of years ago. Stars that found a way to cheat the clock, to steal time from the universe, to burn bright when everything around them was fading into the long, quiet twilight of old age. They are the blue stragglers. And they are one of the most beautiful reminders that the universe, even at its most ancient, is never truly finished creating something new. Thank you for joining me on this journey tonight. If you found this exploration fascinating, a quick like or subscribe would mean a lot to me. It's a small gesture, but it helps this channel keep growing so we can keep exploring the cosmos together. And remember, the next time you look up at the night sky, you're looking at a universe where even the oldest stars can be reborn, where time can be cheated, not through magic, but through the raw power of gravity, physics, and the extraordinary things that happen when stars don't have to face the universe alone. Good night, and may you never look at an old star the same way again